Hey everyone, welcome to P99 conference. My name is Sagy Volkov. I'm going to be talking about why storage is important for Kubernetes and show you a few methods of how to test storage performance in Kubernetes using a little open source project named Sherlock that I wrote a while back. Let me do the 30 seconds intro about me. I'm a performance architect. I work in a company called Lightbits. Lightbits is actually the fifth startup that I've joined. My main mantra when it comes to performance is always to try and tune what I'm displaying, whether it's numbers, graphs, or whatever, to the audience. So it will be interesting. And last and definitely not least, I've climbed 18 out of the 58 14ers that we have in here in Colorado. These are mountains that are above 14,000 feet. So that was about me. Let's continue on. So storage performance on Kubernetes. Initially, Kubernetes was all about stateless application, but then more and more companies started to use it for stateful applications, and then eventually the big enterprise companies started to use Kubernetes as a platform. More and more of these are now pushing whatever applications and workloads they had previously outside of Kubernetes into Kubernetes, including tier 1 and tier 2 applications. These are the ones that have heavy SLAs. When you write something to the storage, that transaction needs to be there and forever. This type of application. For these companies, the performance of the storage is becoming now kind of a metric that they need to look into. Again, they have SLAs to whatever applications, whatever tier of application they are running, and they have to adhere to these SLAs. So understanding not only your compute power but also your storage performance is something fundamental. By nature, Kubernetes looks again a little bit more about the compute side of things and the network, less about storage. And I guess the main reason is that, there are storage solutions that lives inside a Kubernetes cluster, call it converged or internal to the cluster, but there's plenty of legacy storage or newer software-defined storage like Lightbits that resides outside of the Kubernetes cluster, and of course all of these methods use CSI to connect to the storage. But we still need a way to test this performance behavior of the storage. So why Sherlock? Well, the name is just a nice thing about being a detective and trying to solve things. It started basically as a project actually in my previous company in Red Hat, where I needed to show performance of a software-defined storage solution in OpenShift, and the customer didn't want to see anything has to do with traditional synthetic workloads like VDBench or FIO. They wanted to concentrate on what they call real-life workloads on databases, which of course, even running a database with any kind of a workload generator is not really real life, because it's not the data that that customer is actually using or you are using, but it's a projected data of how things should look in real life. For a lot of the enterprise or large companies that are maybe just getting into Kubernetes, it can be intimidating and complex sometimes to deploy a database in Kubernetes. Yes, operators really help with that, but once you want to do things with test things on the storage level, you want to deploy a lot of these, and you want to deploy it in a fashion that It helps. It's like more equal across the Kubernetes cluster. That's Sherlock is kind of doing a lot of this heavy lifting. Eventually, Sherlock became a tool that plenty of people used it to show performance in Red Hat, and I do the same thing now in my role as a performance architect in Lightbits. Let's pause a little bit and talk about why NVMe TCP and why Lightbits. So Lightbits, we are the folks that wrote the spec for NVMe over TCP. We are the people that initially wrote the NVMe TCP module for Linux. It exists in the Linux kernel since 4.10. You can easily backport it if you need to earlier versions. Of course, throughout this process, this was 2016, 17, other companies and developers have joined and showed interest in NVMe over TCP. So a lot of people contribute to the protocol, to the spec, to the kernel module. Lightbits by itself is pretty much the only software-defined storage solution that provides performance that is as close in terms of latency to local NVMe storage, and even enhance the IOPS performance more than local NVMe storage. We have our own elastic RAID, which is erasure coding protection at the node or server level. We also have an intelligent flash management to enhance the writes and the reads from SSD-based devices, of course NVMe SSD-based devices, basically enhance the life cycle of these devices. And of course, we have all the core storage people that you would expect from a storage solution. The resiliency, the snapshots, the clones, compression, all these kind of things. So storage performance, let's talk a little bit about this. Mainly three things that are interesting to people. Latency, as in how fast it takes my query from the database to get actually the results back from your storage. The IOPS, which you can translate in a database world, so how many transactions I can actually push in, and the bandwidth that I can use. Of course, at some point, IOPS and latency starts to kind of hit each other or interact with each other. The more IOPS you push in, your latency usually go higher. It is your kind of game in terms of tuning the storage or your whole platform to whatever application you need to run. Just two very important points that I always tell people when they test storage. You make sure that you test the performance when the storage is under duress. That means your storage platform lost a device, or lost a server, or lost a switch connected to it, something like that, because you want to understand how it behaves in those times. And also always measure the recovery time of your storage. Again, you lost a device. How long does it take for your storage product or storage vendor to actually recover from that? What's the impact on the performance of your application while this is happening? And I would recommend to test these things with and without stressing of the storage, to actually understand the difference. You want the gap between having kind of a recovery time without stress and with stress to be as small as possible. Software-defined storage solutions are network sensitive, so always make sure to measure your network even outside of the scope of storage before you start to measure the storage itself. So now let's talk about Sherlock. Right now, currently, Sherlock supports 4 types of databases. and 3 workloads. I am in the process of adding more, and of course, you guys can feel free to enhance the project and add your own things. Right now, you can test PostgreSQL databases using either pgbench or sysbench. You can test MySQL with the sysbench. You can test Microsoft SQL Server and hammering it with HammerDB, and as well as MongoDB with YCSB. These are kind of all the options that you have. Right now, the way Sherlock is designed is for you to test only one of these type of databases at the same time. So 100 Postgres database pods or 20 SQL Server pods or something like that. It is easier to test any performance, definitely storage, if you kind of isolate it into a specific workload or a specific database. However, in the near future, you will be able to test it with a variety of databases that runs in parallel at the same time. The output will be a little bit maybe weird to look into, because what HammerDB is using and how it's using the CPU is completely different than how sysbench, for example, is using the CPU. But it will be an interesting option that I'm going to add. Right now, Sherlock is written in Bash, mainly because when I wrote it, that was the demand from the customer. I am working slowly in basically creating a parallel version of it running in Python. I had a few people asking me about this. But, beauty about Bash is that it exists today on any operating system, even on Windows. It's easy to run this. Sherlock basically, as I earlier mentioned, kind of does the heavy lifting of making sure that it's not only easy for you to deploy all your databases and populate the data or insert the data into it and then run the actual workloads, but it also doesn't count on actually the Kubernetes scheduler to schedule equally all the database pods. So actually, when you create the databases, they are created in a sort of a serial fashion in terms of how to push them into the worker nodes in Kubernetes. And again, the idea here is that you will not only test the storage, but also test your Kubernetes cluster or your worker nodes. How do they behave with X number of databases running on the Kubernetes cluster? There's many options for Sherlock. We'll go into that later on. And as I said, right now it's written in Bash. Run it from Linux, Mac, if you have Bash on Windows. All basically that you need is either a kubectl or OC if it's OpenShift, and a network connectivity from whatever VM, instance, workstation, laptop you're running into the Kubernetes cluster. That's basically all you need. Let's look a little bit about the layout of this project. Again, everything is on GitHub. There's a databases directory. That's where the scripts to create databases and then run workloads on these databases, which will divide into the section of inserting data into the databases versus actually running the workload. There's plenty of a configuration file. There's a configuration file directory that you can use to specifically if you want to just do MongoDB or you just want to concentrate on MySQL. All the containers that are basically running in Sherlock are all the code for that is under the containers directory. There's a benchmark container that basically runs all the workloads. There's still a method in Sherlock to run FIO from many pods. So it's kind of like taking the good old FIO method and placing it in a container that again is doing Sherlock is doing all the heavy lifting in running a lot of these. And there's a small container that I wrote in order to collect the statistics from the worker nodes while running. And also, if you happen to have an SDS that runs inside the Kubernetes cluster, you can specify that as well, and there will be other statistics that will be collected just from those nodes that are running the SDS solution. And as I said, FIO is still there. So about the configuration of Sherlock and the whole layout. Remember, we're testing storage. We're testing it with an application, which in this case is a database. So when you do that, your Kubernetes cluster should be as idle as possible, meaning, don't run any heavy workload that actually might take CPU resources or memory resources or network resources from the worker nodes. We want to, for this duration of whatever we are running right now, just test the storage. So let's make sure that, kind of the cluster is clean. Only the basic Kubernetes system pods and deployments are running, and the rest is for the databases that we are running. You should try and make sure that all the worker nodes are equal from a hardware perspective. The main reason behind this is, and again, we are trying to make every worker node run the same workload times X times in parallel. And if if you have, a 20 worker node cluster, 5 of them has 96 cores, CPUs, and 15 of them has 32, that is going to be hard. The way that Sherlock right now is, looking at things, it's in a very simplistic way, taking into account that the hardware is the same, and basically spreading equally all the pods on them. If you do have like a problem like I just talked about, of some nodes with 96 cores, let's say, or more RAM, and others with less, then make sure that when you do the calculation of how many databases, how many resources to give them, just take into account the lower end resources, and it will do the same thing on even the higher end resource nodes. Equal number of databases will be deployed. That's one of the key things. We want to make sure that all your worker nodes are trying to send the same traffic. Of course, it's all random, but kind of the same type of workload at the same time. Same number of PVs and the size of them. So each database will be created with whatever PV size PVC size you choose. You're gonna have to do some sort of, as I said, some sort of a calculation of how many databases you can actually deploy per your worker node and how much resources to give to each of these pods. Usually, I like to leave 25% of the resources of the worker nodes off, just, also for real life, because Kubernetes has its own thing that needs to be done. And also, if you have 100 nodes, if you have 100 worker nodes, you lost one, you want to have that gap that the applications can migrate into the other 99 available worker nodes. So this is a kind of an extract of a sample of a config file. This is for Postgres running sysbench. So there's a lot of variables in here, and basically one of the most important one is, of course, to supply whatever binary you're going to use to drive everything, whether it's a kubectl or OC or whatever. You're basically going to supply the hosts that are your worker nodes, the host in case that you are running inside Kubernetes that are running your software-defined storage solution. You're gonna basically say how many worker nodes you have, how many database per worker node, all these kind of things that I've talked about, your resources, PVC size, things like, that are getting more down into the details of the workload runtime. This is marked as 5 minutes. That's usually what I do for when I want to test things. If you really want to test storage, 1 hour and going up to 12 hours should probably be what you are looking at. You want to see, how the storage subsystem behave for long durations. You don't have an application to just write 5 minutes a day. Usually it's a lot more than that. Especially and nowadays everything is based on flash or SSDs. You want to see how things behave in that manner for the longer duration. The rest of the things here are again more specific for the workload. In this case, it's sysbench. So we can actually try with sysbench to impact, the ratio between the percentage of reads that we're going to do from the storage and the percentage of writes that we're going to do to the storage. And with sysbench, you kind of basically do a ratio of the number of inserts per 10 transactions or updates and things like that. If you keep the ratio that here on the screen, it is very close going to be to about roughly 70% reads, 30% writes. All sorts of other variables in here. I'm not going to go into all of them. The GitHub page explain of them, but they go more into limiting also the workload pod that is running, the interval of the statistics that we're taking, and things like that. So this is basically how you like a screenshot of how you will deploy a database. You'll basically supply the previous config file that we talked about, and basically Sherlock is going to go and say, okay, these are all my worker nodes. This is the type of databases that I want to run. This is how many databases per worker nodes, and start to build all of that in your Kubernetes cluster. As I said, we're doing it in kind of a serial fashion per worker node. So if you have 500 worker nodes, it might take a little bit more time to deploy all the databases. Again, if you choose playing with how many resources each worker node has, if maybe you chose to only deploy a single Postgres on each of the worker nodes, things to create the databases will be a lot faster. But I've seen people playing with this and doing like 10 databases and even 50 databases. Very small databases, but 50 of them that are running. But that will be the method of how to create databases. Your next step is basically to run whatever workload you want to run and load the data into it. In databases, even in synthetic workloads, you have a phase where data is being recreated. But in databases, workload generators, usually the data is randomly created. It might take time to create it. That time will greatly be impacted by your CPU resources on your worker nodes, because at this point your worker nodes are running the application generator or workload and your database. But that is basically how will you load the data in. In this case, the example is for running a sysbench. So it will load the number of tables that we saw here in number of tables, per databases, how many rows, and all these kind of things. That's the loading data section. And then the final thing is running the actual workload. And again, in this example, we are running basically sysbench. We're using the config file that we wanted to provide. And what you can see here is that we start to collect stats on all sorts of on our worker nodes. This example is actually even from OpenShift Container Storage, so it's using Ceph, and eventually the workload itself, sysbench, will start to run as well, and basically everything runs as jobs. So once everything is done, remember we set a time. In this example was for 5 minutes. Once all the workloads are done running in parallel on all the databases, basically the Sherlock will retrieve all the logs from all the pods, the pods that run statistics, the pods that run the application workload, and even the database pods, collect all the information, gather it, and create some sort of a summary. And now I will show a live demo of the performance that you can get with PostgreSQL using sysbench on a Kubernetes cluster using Lightbits as the storage provider. Okay, folks, so let's try to do sort of a live demo since this is recorded. I have here a Sherlock configuration file for PostgreSQL. As you can see, I have 20 worker nodes. I'm going to put about 6 database pods per worker node. These are configuration of the memory size, CPU that I'm allowing for per each Postgres pod, PVC size, all sorts of things. These are sysbench parameters. 250 tables of 1 million rows is roughly about 50 gig on the file system. Down here I have also a sort of an array that holds mapping of network adapters on the worker nodes, because these are going to be monitored by Sherlock to understand the bandwidth and how much data is actually being pushed over the network. So let's go ahead and run this. And I gave a workload runtime of 10 minutes. Well, I'm not going to wait the 10 minutes. I'll pause the video, and then I'll come back once this is done. Okay, folks. So the live run of Sherlock is done. I'm just going to run the print results script. I provided it with the directory where what we named the run. This is part of a single run, not of a loop, because you can also do loop and it will average that. We're going to print it simply. You can put it also to a spreadsheet if you want. Type of benchmark we use is a sysbench and our config file. And what we see is, from 120 databases, we got about 9.2 million transactions. You have the transaction per second for all the databases. It's kind of an average of an average. And you can see per pod, basically, and per worker node, also the amount of data went through the network devices, and also the IOs that went to the physical NVMe over TCP devices that Lightbits attached into these worker nodes via CSI. That's the end of the recording. I'll stick around for more questions now and later on. I hope you enjoy it. Thank you. So the demo is done, and I'll be happy to answer any questions, and I hope you enjoyed this session. Any questions, you have my email, my Twitter here, and if you want to join and participate and enhance Sherlock, feel free to do it and contact me. Thank you very much.